So let me make a split screen. All right, so if you didn't draw something from 0 to 14, I know that there are things that can be, above and beyond, but this is our general pH scale. At the middle, what would you say about the concentrations at 7? What would you say about the concentrations of hydronium and hydroxide? Yeah, that's neutral, but what would you say about their concentrations? So equal numbers of OHs and H3O pluses, because the acidic part of the thing and the basic part of the thing should be equal, right? Because it's neutral. They cancel each other out. You need to write here, hydronium concentration equals hydroxide concentration. What does that bracket mean? Molarity, right? That is the point at which they're equal. That is the only time at which they're equal. That's why it's pH of 7. So what is greater at pH 0? Which of these? Hydronium, right, the thing that's acidic. Because these two are fighting, right? The hydronium is yielding acidic concentration, or acidic solutions. Hydroxide is yielding basic solutions. So you have to know that. Acidic means lots more hydronium. Oh, and sorry, and they're at pH of 7 also, right? 1 times 10 to the negative 7th molar. Because both of these are equal to 1 times 10 to the negative 7th molar. That negative 7 should resonate with you because we're at pH of 7. So those exponents actually are showing you the pH when you are talking about something of base 10. Talk about logs in whatever, algebra 2. Base, like log, base 10, x is equal to a number. 7 is that number. I forget how to explain it via algebra, but that's right. Okay, so the other one, 0 is going to have hydronium is greater than hydroxide. Sorry, my inequalities are in the middle, but it's greater than hydroxide. You got what I'm saying here? So give me a number that hydronium could be. So I'm going to say hydronium could be 1 times 10 to the negative what? Let's go negative 6. I like that, okay? If that's 1 times 10 to negative 6, what is hydroxide? Negative 8. So what are you doing with your exponents? Huh? They adjust because they have to be equal to what overall? 14. So if this is hydronium and negative 6 plus blank equals negative 14 according to which pH formula? Which of those pH formulas equals 1 times 10 to the negative 14? Hydronium times hydroxide, right? When you multiply those two concentrations together, they equal 1 times 10 to the negative 14. This one's the hydroxide one that we just talked about. Okay, and last one, which is greater at pH of 14? Hydroxide. So hydroxide is greater than hydronium, and you can tell me an example concentration of hydronium here. 1 times, so hydronium concentration is going to be very low over here. Very low means pH of concentration of 1 times 10 to the negative 4 is actually pretty. That's like 0.001. That's a pretty big number for a concentration. Negative what? That's even larger. See, negative 10 to negative 2 is larger than 10 to negative 4th, right? Negative 10th. Okay, so 1 times 10 to the negative 10th. That's 0.00001. Right? So we want hydronium to be low, low, low. And if this is 10 to the negative 10th molar, what will hydroxide be? That'll be to the 10 to the negative 4th. Because they complete each other. Because they're always there to equal 1 times 10 to the negative 14. Yay! Okay, so you got that concept. Good. We can do the pH formulas in a second. What does strong mean? Anybody? Fully ionizes 100% of the time, right? We're going to talk about how that contrasts to weak bases and strong bases in just a moment. What are the 6 strong acids? Don't look at your notes. Try not to. Nathaniel, go for it.
Nitric acid.
Okay. Sulfuric acid, shout them out. Hydrochloric acid, I hear you. High, okay. Hydrobromic, and I heard one, it just didn't come all the way out yet. Perchloric, HClO4, good. And then how do you know the 8 strong bases? Lowercase b on the periodic table. So how many from group 1A? 5. How many from group 2A. 3. Those CBS down there. Or not CBS. Yeah, CBS. Calcium, barium, and strontium. Okay. We already talked about the definitions yesterday. We'll go over the rest of these here soon. Conjugate acid, conjugate base, we'll go over. Let's talk about pH now. Let's go through your pH calculations, okay? I want to go over the ones that you guys were really struggling with first, so that we can kind of clarify our own misunderstandings. So from this one, number 2, tell me your process here. Morgan, how did you know where to start? Okay, so what is the given? It's secret, right? Beautiful. Do you need me, Miss B?
Well, I was wondering if you had a radish.
Oh, yes. Hold on. I put them in Melissa's room. Never mind. They're, in the back corner where they are in her room. In the back corner, so like back near the, the plant light over there. If you walk into her room, they're in the back corner. She got AP. Okay, anyway, so hydronium. You know if it's acidic, this is a strong acid. This is HNO3. HNO3 is one that's going to 100% ionize to H pluses, which is really all we're dealing with, what we're concerned about. So this is telling you the concentration is 0.75 molar. Okay, then what did you do?
I just plugged that into the formula that I had.
The formula that has that you're using in the formula. So what's that formula?
pH
The hydronium. And you plug that in, what did you get?
0.125.
Okay. pH has no unit, okay? Yay! I can't yell at you for your units on pH. Okay, so no units. So just that's 0.125. You got that. Okay, some of us did not get that far. The other one I saw that we had a lot of problems with was it 4 or was it 6? 6, do I need to go over 3 or 4? Tell me now. You need to go over this at all? Okay. 6. We did 5 in class. Okay. 6. pH of 9.6. Okay, so pH of 9.6. Before you solve, predict if the concentration will be greater than, less than, or equal to 1 times 10 to the negative 7. Tell me right now, I know we are all very comfortable with determining if something is acidic, neutral, or basic on the pH scale. The pH scale you've dealt with a long time. The pOH scale is a new thing for us. So according to this, is this acidic, basic, or neutral? Huh? Basic, right? This is basic. You know the pH scale runs A to B, yeah? Alphabetical order, acid to base. Just make sure you know that. Okay, so this is basic. If it's basic, does that mean we have more hydroxides or more hydroniums? Why hydroxides? Because that's what's causing it to be basic, right? So, hydroxide is greater than hydronium. Okay, at neutral, what were their concentrations at neutral? 1 times 10 to the negative 7th, right? Because 7 is pH of 7. So at neutral, they're this. So, which concentration will be greater? Will the concentration, that's probably what you're trying to find. Will the OH concentration be greater than, less than, or equal to that? So the OH concentration will be greater than 1 times 10 to the negative 7. And then you probably had to solve it. It was probably approximately 1 times 10 to the negative 5th, maybe like, I don't know, 7.1 times 10 to the negative 5th. Did somebody solve that? Okay. I try to make up the front number. I know I can always do that. Front number's harder. Okay, so hydroxide is 3.9 times 10 to the negative 5th. So what was hydronium? Anybody solve that part here? 10 to the negative 10. Molar. Okay. Anytime you have a concentration, put molar, because that is truly a concentration of something, okay? So 2.5 times 10 to the negative 10th, 3.9 times 10 to the negative 5th. Those exponents and these they're about negative 14, so you kind of can check that you're correct. Yeah.
Okay, I got those numbers, but I don't think.
Did you do a negative 10th or negative in the front? You should probably put your negative in the wrong place when you're doing your logs. It's like knowing your pH here, you're gonna go 10 to the negative pH. So anti-log 10 to the negative pH, so 10 to the negative 9.6 will give you hydronium, which is 2.5 times 10 to the negative 10th molar. I think you should probably put it in the front first, the versus the exponent. Yeah. I listened to Emily, but that's how she got it, I'm sure. Oh, yeah, thank you. So if you take, I would start with a pH and go to find POH. So if you take pH, what's POH? You can do this part in your head. You know the pH is this. POH is, tell me the math you're doing. 14 minus 9.6, so it should be 4.4? Yeah? Okay. So if the pH is 4.4, how would you find OH directly from POH? Okay, so the OH concentration is 10 to the negative POH. So when you do 10 to the negative 4.4, apparently you get 3.9 times 10 to the negative fifth. I got something close to that. So, okay. So you once you start to use these pH formulas, they kind of start to just kind of click, and you know what to start using, especially when you're given special circumstances. So these were the homework ones. I'm just going to let you guys check these. These were all strong acids and strong bases. So sodium hydroxide, sulfuric acid, lithium hydroxide, nitric acid, calcium hydroxide, hydrobromic acid. Those were all yours, yeah? Yep. Okay. Those are all strong acids and strong bases. So that's why you're allowed to assume the concentrations of hydronium and hydroxide are what they are as here. Did any of these have the problem where you had to multiply the hydroxides by 2? Yes, calcium hydroxide. It's the only one that's dibasic. Calcium hydroxide. So whenever it ionizes, it makes calcium 2 plus 2 hydroxides. So that big 2 is like, I need to multiply the hydroxide or this concentration by 2 before I can actually begin. So make sure that you're just wary of that. So your solutions, oops, where did I put the solutions? They're right there, okay? Did you need to check these? If you did the homework problems, then you can check them. Yeah? What's up? So check yourself. This is the concentration. Actually, I think you guys can figure out which is which here, based on your answers. It should have been hydroxide and hydronium, I think. I can't remember what I phrased the question as. There it is. Calculate the hydronium and hydroxide concentrations, yeah. Those of you checking, is there something that I need to go over one?
For a lot of them, I got the right number but the wrong type of stuff. Like all.
With anybody else? I think that's a calculator issue for you. Maybe. I don't know what you do. I can check I'll check over your work. Because it's probably just something silly, like you're putting a decimal wrong, or log, ln, log, something like that. Alright, I'm going to scroll down a little bit more. Yeah.
Did you get 2B?
Will I do 2B? Yeah. 2B, okay. Number 2 had the sulfuric acid concentration of 0.0025 molar H2SO4. Okay, sulfuric acid is just a strong acid. I did not tell you to multiply anything by 2. It's something very simple. It is diprotic, but don't think of anything too much past that. This is the concentration of hydronium. So pH is negative log of 0.0025, and I'm going to just calculate that again. I'm guessing it's just Oh, okay. So then your pH is just whatever this is, 2.6. Another one I need to do, guys. That was just number 1. I did the pH of number. I did the pH of number 2, the sulfuric acid. Yeah.
So for one.
Oh, either one.
Oh, for one, do you like when the H has a subscript of 2, it's an acid, you don't multiply it?
Only because acids dissociate in a stepwise fashion. They're different than bases. Bases are like pop, done, out, make 2 hydroxides immediately. Acids lose 1 H, and then they go for a while, and then they lose the other H if they're dibasic. That's like a more advanced thing, and so I don't talk about it here. But yeah, just assume it's just a normal acid, doesn't do anything different. Okay. Ariana?
On number 2, I thought I needed that should be
2F. Was this your hydronium? That was, no, this is hydronium. That's hydronium, right? Did you switch them? Okay. Any others I can go over right now? For anybody? Yay, nay? Nay? Yeah, okay. Take a second more. And then we're going to talk about weak bases and indicators for like 10 minutes. And then we'll be good. It takes a little bit more practice. Usually after 2 days, pH formulas start to sink in. Yeah. Your big test in class? No. Yeah, don't. Yeah. We're going to talk about that not today. Is that okay? It's an experiment that you set up between acid base and reactions. Grab the CR cable. I gotta set you up. Okay, let's start with indicators. Please start writing down a couple notes, and then I'm going to walk you through a couple of examples. But first, write down indicators, because they are used in today's lab. They're used in today's lab and the lab for conservation. You for starting this without any first moment. Color is awful. Alright, so we're going to use probably, in total, 5 different indicators this unit. And they're really cool. And I actually showed you one way back in the day when I was doing chemical changes. And from unit 1, you remember that easy stuff. We saw how different chemical properties allow for indicators to change color. Well, we're going to see that today. We are using, let's see, actually, tomorrow we're using litmus paper. Litmus paper, it's like literally paper, like a little strip of paper. It starts off 2 different colors. I have 2 different varieties of it. I have red litmus paper and I have blue litmus paper. And when the blue litmus paper is exposed to an acid, it changes color. And when it changes color, that's indicating to you, hey, I have an acid here. I have lots of hydroniums. And they're attacking the paper and they're making it this color. But if I take the blue litmus paper and I put it in a base, it doesn't do nothing. It stays blue. Okay? So these different color changes are indicating to you something about the substance, aka its pH. It's an acid or a base. So it's literally what an indicator, what the word means. It's indicating something to you about that substance based on color changes. So they're really cool. They're really pretty. My cheesy jingle. I'm not gonna not gonna jingle it for you, but I'm gonna try here. I'll jingle it for you like this. Blue to red acid, red to blue base. Okay, so this is my way of remembering blue to red acid, red to blue base. Okay, you can kind of jingle that to yourself. This is how you remember which color litmus paper is in an acid and a base. You got that? It's like red acid, red acid. I don't want to say it like a real basic girl, but you know. It's like red acid and blue base. Okay. That's how it is, okay? And then we're going to deal with that tomorrow in the lab. So another lab we're doing, which is a titration on Tuesday. It's using like the most expensive piece of equipment we own here. Your whole setup will be like over $200. No pressure. All right, stay with me. Phenolphthalein. Phenolphthalein. You don't have to spell it right. It's cool. Phenolphthalein. It's got some like weird pHs and stuff in there. All right, so phenolphthalein is really just clear in all circumstances from pHs 0 to about 7.5. Okay. After it reaches above 7.5, it starts to change, little like hot pink magenta, but it's really transient. It's gonna change and then turn back and change and then turn back to clear. But once you're at pH of 8 and higher, it's gonna be like magenta, pink in your face. Okay, that means we have met something called the endpoint of a titration when it causes that color change, because we've gone past neutral point and we've started going to the basic region of the pH. Or the pH changes that are going to occur. So phenolphthalein works really, really well for showing a specific pH. Like we are at pH of 8. But this one, it's like, I'm in acidic region. I mean, I could be anywhere from 0 to 7 to about 7. Or I'm in basic region. I can be anywhere from like 7.5 to 14. This one's less helpful in number form. It's just like, it's acidic or basic. This one's like, hey, I'm above 8 now, okay? So it's a little bit more helpful. And you can see that the magenta color here is pretty, like, glaringly obvious you've met phenolphthalein's equivalence point. All right, so I got 2 more indicators to tell you about. Ready? Okay, most of us look like we're good here. Well, actually, let me tell you about a couple more. There's like 6 here. So any indicator you want to use, you have to deliberately choose it, because a lot of times we want to see a color change at pH of 3. So if I want to see a color change at pH of 3, which indicator has its color change at pH 3? Thymal blue, right? So thymal blue, it starts to change. Well, it's actually about 2 bromophenol. No, so bromophenol blue changes at about 3.5, maybe. So we have to kind of play with the indicators to figure out which one we want to use. If I wanted something to change at pH of 8, we just talked about it. You see, phenolphthalein, it's colorless and it changes at about pH of 8 to pink. If I want something changed past that, I can never say this one, Alizarin yellow R, it changes at pH of like 9. Okay, so we've got all these lovely indicators, and these are all chemicals that most of them have in the back in our stockroom, right? But we also have indicators in nature. So you've seen hydrangea flowers, they're pink and blue and purple. If you grow them in acidic soil, what color are they? Good job, guys. Okay, pinkish red. If they're in basic soil, pH above 7, they're blue. Okay, they're like litmus paper. They change color in pH. It's kind of cool. And if you want neutral, you put them in purple. If you want purple flowers, you put them in neutral soil. Okay, but all of these things are indicators. If you ever want to try and impress some people with your vast chemistry knowledge, get some blueberries or cherries or plums or radishes or tomatoes, and they change colors in different pHs. It's kind of cool. Okay, we are using the famous cabbage juice today, okay? Cabbage juice is an indicator. It starts off, it's red cabbage juice, okay? Red cabbage juice, when you boil it, smells like farts. It's great. It stunk real bad in here like 2 days ago when I was doing that. Starts off purple in a neutral form. It's going to change kind of like reddish, pinkish in color for the acidic realm, and then up to like a couple different colors I want to tell you about. Different colors in the basic realm, okay? So what you're going to do is you're going to set up some spot plates. There's these little plates with different holes like this on them, and you're going to test known solutions. And I have some buffers. The buffers are actually pHs 2 to 12. Your lab, you only need to do maybe 4 to 10, but I'll just let you guys follow the lab instructions. You're going to put some pH 2, 3, 4, 5, 6, all the way through 12, okay? You're going to put those known concentrations here, only 5 drops of the buffer, okay? I had to change the lab instructions to eliminate some waste. So 5 drops of known buffer. Then on top of that, you're going to add 10 drops of cabbage juice. CJ, cabbage juice. So you're going to add cabbage here, here, all the way through, and you're going to see different color changes occur because of the different pH known solutions. And that is your answer key, okay? That's your answer key. After you do the knowns, you're going to then set up another plate with all the circles on it, okay? Set up another plate, and you're going to put unknowns in those. The unknowns are things like kitchen cleaner, shampoo, Sprite, baking soda, Tum solutions, things like that you don't know their exact pH, but you might know some, like, oh, it's basic or it's acidic. So once you put those unknowns in there, they're also only going to be 5 drops. You put them in there, and then you put the cabbage juice on top again. Okay, there's cabbage juice on top. It's going to change the color. So let's say it changes red. You go, okay, well, which of these colors was red? Oh, pH 1 was, or pH 2 was red. This Tum solution must be pH of 2. Do you see how you're checking yourself against the answer key with colors? It's really cool. Now, don't just say red. You're going to go, oh, it's cherry red, or it's lavender, or it's periwinkle, or you got to give me some girly colors up in there, okay? Because they're going to be kind of similar. All right? So let's go groups of 3. Can you show where the key is? Start off the outside tables, and then we'll go in here and we can stop. Start at the perimeter, and then we'll come back and I'll fill in Start off with groups of 3. Please not make me say it again. Groups of 3. Over there. 3. Kyla and Aaron. Is Aaron here? Daniel's there. Alright, I'm gonna have you load it. I'm just saying on the table, that station. I just need it. I'm gonna touch station stuff around. 2 people here. Alright, and let me give you some tips on how to get this done. I want your attention in 5, 4, 3, 2, 1, ready? Okay, tips on getting this done. You will need goggles, just coming here up in just a second. What I would do is assign one person to be the known sample people. The known samples are here in order, they're in order. These are the buffers from pHs 2 to 12, okay? This is where you come and you're going to bring your little spot plate and you're going to go, okay, drop, okay? And you need to remember which pH is which. You're going to send another person to the unknown table. These are unknown, and those are unknown. There's only like 7 or 8. On the last sheet, it might say there's more. Don't worry about it. These are all I have here. These are labeled. And what I would do is have a piece of paper write down. The first column is Tum, Sprite, shampoo, ammonia, lemon juice, blah, blah, blah. Okay, so one person does that. The next person is going to be at the table getting ready to put the cabbage juice in. You see the cabbage juice at your stations? It's purple solution. You have 3 people, you got 3 drops.
Don't forget.
Oh, sorry, I didn't. Oh, I'm so sorry. Okay, I'm like, right, that's your here.
Both sides of the same.